A mass spring system is quite simply exactly what it sounds like. It's a system made up of a mass and a spring. So much like when we looked at things like Hooke's law, where we would suspend a mass on a spring and then let it remain at equilibrium, now we're going to look at the dynamic case, which is the case in which it's moving. So if you hang a mass from a spring and then you pull down on it, as you have in this second picture, and then you let go of it, that mass is then going to start to bounce up and down. Think of like a bungee jumper who kind of has jumped off a bridge, and after that bungee cord has been fully extended, it's going to pull them back up, then gravity pulls them down, then the bungee cord pulls them back up, and it's this repeated motion. So the person in that case is just serving as the mass, and the elastic cord is acting like the spring. So when you have a situation like this, we call it a mass spring system. And the equation for analyzing the period is very similar to the pendulum equation with two variables kind of substituted out. So t is still the period of the mass spring system measured in seconds. However, it's 2 pi square root of the mass at the end of that spring divided by the spring constant, which is how stiff or soft that spring is. A low spring constant means it's kind of like a slinky, right? It's very easy to stretch. A high spring constant would be like the shocks in your car, much more difficult. No matter how hard you pull on that, you're probably not going to extend it very much. All right, so let's just use that equation and we'll try and apply it here. So in this case, we have a 2 kilogram mass that's hung on a spring. And when we hang it on the spring, that's that case on the left. Just being hung on the spring, that spring has a length of 6 centimeters. Then somebody pulls down on this and stretches it to about 18 centimeters. So they've pulled it down a total of 12 from its initial case. They're going to let go of that, and that spring, mass spring system is going to start to oscillate up and down, up and down, up and down. Now the spring constant of this spring is given as 800 newtons per meter. And the questions that we have are what are the period and the frequency of this object's motion? So we know that the period of a mass spring system is represented with 2 pi square root of m over k. So in this case, we can quite simply just substitute in the values we're given. So 2 pi is a constant, the mass is 2, and the spring constant is 800. So if I plug all that into my calculator, we should find that the period is 0.31 seconds. So a little bit under a third of a second to complete one full up and down cycle. And that kind of makes sense. It's a pretty high K value, so it's a pretty stiff spring. It's probably going to kind of cause this motion to occur. It's going to vibrate pretty quickly because it's not like a slinky where it's really going to stretch out and come back in and stretch out. It's a pretty thick spring, so it's going to kind of oscillate pretty quickly. If we want to find the frequency, hopefully we recognize the fact that the frequency and the period are just inverses. So if I take the inverse of the period, that's 0.31 seconds, I'll get a frequency of about 3.23 hertz. Kind of makes sense. If it takes a little bit under a third of a second to complete one cycle, then in 1 second, it's going to complete a little over 3 complete cycles. If we want to look at a second example, this one's a little trickier. We're given the spring constant again. We're told that this mass is pulled down 15 centimeters, and then someone lets go of it, and it begins oscillating up and down with a frequency of 0.18 hertz. So the question becomes, what mass must be on the end of the spring? Because if the spring constant is 20 newtons per meter, there is only one mass that will actually oscillate at exactly 0.18 hertz, and we want to find that mass. So the first thing we probably want to do is convert that frequency into the period, because then we can use our period of a mass spring system equation. So if the frequency is 0.8 hertz and we take its inverse, we can find that the period of this mass spring system is 5.55 seconds. Now I can plug that into my mass spring system period equation. The period of 5.55 seconds is equal to 2 pi square root of whatever that mass is, divided by the spring constant of 20. So now we can just make sure we solve this algebraically. I'm going to do it all kind of at the end, but I'm going to divide both sides by 2 pi. Then I'm going to go ahead and I'm going to square both sides to get rid of that square root. And then I quite simply just need to multiply both sides by 20. And if I do so, we should find that that mass has to be about 15.6 kilograms. Once again, be very careful when you divide by 2 pi. If you don't ensure in your calculator that that is in fact in the denominator by using parentheses, for example, you will get something like 1,520 kilograms, which is obviously far too high. So please be very careful with the 2 pi. It's one of the only things that's really going to trip you up if you're not very careful.